Standard physics textbooks often start with this image. A single beam of light strikes a mirror, reflects, and forms a perfect symmetrical V shape. This model accurately predicts where light goes, but it glosses over the physical mechanics driving that movement. To see the mechanism, we have to look at the three-dimensional reality. In this diagram, a single line expands into a wavefront, a vast plane where every individual wave oscillates in phase. The straight rays we usually draw are simply arrows indicating the direction this massive surface is moving. When this wavefront hits a mirror at an angle, the edges don't make contact simultaneously. One corner strikes the surface while the rest continues through space. Analyzing the fraction of a second when light is partially touching the mirror exposes the geometric engine behind the law of reflection. This is a schematic of an incident wavefront, labeled AB, angled toward a reflecting surface, MN. Right now, only point A is in contact with the mirror. Point B is still in the air, needing time to travel the remaining distance to the mirror. According to Huygens Principle, every point on a wavefront acts as an independent source that generates its own secondary spherical wavelet. The moment point A touches the mirror, it starts generating one of these new wavelets, expanding back outward from the point of impact. By measuring how far this wavelet grows, while the rest of the original wave is still falling, we can map the reflection's path. Point B travels through the air at speed v for time t to reach the mirror at point C. We label this distance v times t. During that same interval, the wavelet born at point A expands to a radius of v times t. Drawing a tangent line from point C to the outer edge of this wavelet gives us point E. This line, CE, is the fully formed reflected wavefront, the sum of all the secondary wavelets. This construction creates two specific right triangles, triangle BAC and triangle EAC. Both triangles share the exact same hypotenuse, AC, along the mirror surface. Side BC and side AE are also identical, as both represent the distance v times t. Sharing a hypotenuse and an identical side makes these two right triangles perfectly congruent. Because the triangles are identical, the angle of incidence equals the angle of reflection, a geometric necessity. These same geometric principles govern how light interacts with complex, curved surfaces. Deep parabolic mirrors used in massive telescopes rely on this wavefront geometry to capture light from the distant universe. When a flat plane wave approaches this curve, its outer edges strike the glass before the center. Those edges immediately spawn reflecting wavelets, while the center continues pushing into the mirror's bowl. This staggered timing warps the flat plane into a depressed spherical envelope. As this newly curved wave travels away from the surface, it shrinks and collapses into a single, intensely bright focal point. The macroscopic laws of optics are the direct result of the microscopic geometry of wave propagation.